Thanks all respect professors to listen to this presentation. I am the presenter Zhang from Shanghai Jiao Tong University, and I'm honored to present the paper with the title 3D Geology Scene Exploring based on hand-track somatic interaction. The paper is a result of the cooperation between the Shanghai Jiao Tong University, ZTE Corporation, the Hong Kong Polytechnic University, and the Shanghai University of Sport. The background of our research is the terrain analysis is the basis of geological research. However, due to factors such as distance and range, it is often difficult to study the terrain environment in the field. The 3D terrain module can reduce the terrain range, eliminate the limitation on distance. With properly human-computer interaction, it can meet different research needs. Somatic interaction is one of the most popular methods of human-computer interaction, including tracking eyes, body movements, facial expressions, and gestures. Compared with other somatic interaction methods, gestures has unique advantages. It has the advantage of intuitive, natural, and easy to learn, and do not require special hardware cooperation like mouse and keyboard. The most commonly used human gesture recognition methods are depth-based and skeleton-based. To achieve gesture recognition, depth camera is widely used now. It is a kind of camera which applies reflection-based methods to acquire not only color and position of objects, but also their distance to the camera. There are three kinds of image-forming principles in the market at present, namely structured light, stereo vision, and time of flight. The real-sense SR300 used in our experiment applied time of flight principle. Skeleton-based method can be divided into joint-based and body part-based. Joint part-based methods use a coordinate system to relatively model the position and motion of a couple of joints. In body part-based methods, human body parts are represented by some rigid cylinders connected by joints to form an articulated system. Gestures can be distinguished through the 3D geometry relationship between joint cylinders. At all, the depth and the second date will go through either a handcrafted feature extraction and feature representations or depth learning methods to extract human gesture descriptors. This process combines a few computer graphics and vision techniques such as edge detection, noise threshold processing, and categorizations of human body features. In our experiment, we use Intel's RealSense SR300 to get original gesture depth image. The RealSense SR300 is a real-time sensor camera produced by Intel. During our organization progress, due to slight shaking of hands, some operations, especially rotation, will cause an obviously unstable viewpoint. To solve this, we designed an optimization algorithm. Supported by Intel's RealSense SDK, it can realize gesture sensing with convenient APIs. Combining a depth measuring and a 1080 pixel RGB color camera, the application will detect the shape of a moving hand and then model the hand skeleton, realize skeleton tracing. We constructed the 3D scene assets in 3D Max and then imported them into Unity to get an acceptable viewing experiences. We set up new parameters of main camera, directional lights, shadow, and material shaders. The controlling system is based on Unity's embedded keyboard import events. To fulfill basic operations in the game scene, we mapped the gestural signal with keyboard events. The shaking optimization algorithm I used to deal with the unsteady viewpoint caused by shaking. The procedure will construct a queen with a size of 5 to contain hand cycliton position date. When the depth camera loses the position of hands, it clears the original queen and fills it with new information to avoid date from the shaking position. Every time the position date is requested, the algorithm returns the arithmetic mean value of queen. Optimized hand position will be processed by API of RealSense SDK. There are several embedded gestures in Intel's RealSense SDK. Using these embedded gestures, we constructed new gestures to realize game function. These new gestures are mapped to keyboard event to control the viewpoint or character's movement. We doing our experiment focus on the accuracy of gestural recognition and smoothness of operation. After applying the shaking optimization algorithm for gestural recognition, an overall smoother experience is obtained during inaction. Moving on to date visualization, as explained by figure. The red dot means the original object position, and the blue dot means optimized position. To obtain these results, we use left hand and keep still during analysis. The conclusion can be drawn from the figure that original date had a clear regularity. This is due to maximum resolution of the depth camera. The optimized algorithm reduces the differences in hand positions between each frame, thus making the operation smoother. After designing the algorithm, we set several values for the size of position queen, including 2, 3, 4, and more than 5. However, the optimization effect was no longer discernible. It was decided to finally set the size of queen as 5. We also find out some limitation of our experiment. As the RealSense SR300 uses active near-infrared light as its structured light source, it runs quite well in dark environment. However, when faced with bright environment, such as outdoor scenes, the light will disturb the camera heavily. It can barely recognize the whole pane at a distance of 20 to 30 centimeters. During this project, we experimented and analyzed the feasibility of building a gestural-based 3D scene exploring platform with existing camera hardware and game engine. With conclusive evidence, we proved that this is a reasonable direction of man-machine interaction. As the Internet of Things and smart home became more widespread, gestural controlling will have more numerous applications. Thank you. That's all my presentation, and thanks for your listening. And later is question time.